In this lesson, we take a closer look at the topic of spread and process location and what influence these can have on the amount of out-of-specification parts. And hello again to this lesson, which has one learning objective. In the end, you should know the importance of process spread and process location on the amount of out-of-specification parts. This lesson is divided into two chapters. In the first chapter, we look at different confidence intervals of the normal distribution and the percentage of the population values that fall between these limits. In the second chapter, we look at the impact of spread and the process location on the proportion of out-of-specification parts. Let's start with the confidence intervals of the normal distribution. In case you didn't see the previous lesson, I'd like to briefly repeat the following here. The blue envelope is assumed to enclose 100% of all values. Also, for later calculations, it is important to remember that these envelope curves always intersect the x-axis only at infinity. Exceptions are of course cases where there is a natural limit. So let's remove the blue bars that show the frequencies of each value and next look at some standard deviations. The simple standard deviation is shown here. In our example, this is 0.03 mm. Therefore, the confidence interval extends from the center to 60.07 on one side and 60.13 on the other. The question now is, how many values are between the two limits? Since this is only about the basic understanding, we will not go into the exact calculations any further. The answer is that approximately 68.27% of all values are within plus or minus one standard deviation. Next, let's look at the value for twice the standard deviation. If the single standard deviation is 0.03, twice the standard deviation is logically 0.06 mm. Consequently, the confidence interval now ranges from 60.04 to 60.16 mm. A calculation shows that the following proportion of all values are in this range. 95.45% of all values are in the range from -2 sigma to +2 sigma. Next, let's look at this for the ±3 sigma range. In our example, this is plus and minus 0.09 mm wide and ranges from 60.01 to 60.19. How many values are in this range? 99.73% of all values are in the range of ±3 sigma. This may sound like a lot, but it also means that 0.27% of all values are outside this range. With 1 million parts produced, that would be 2,700 pieces. This is quite a lot and would not be acceptable in the industry for important characteristics. In order to still be able to display the 6 sigma range, the width of the curve had to be reduced. 99.999998% of all values are in the range between ±6 sigma. So only 0.000002% of all values are outside. This requirement seems extreme at first, but is then put into perspective a little. Because with this requirement, you have a safety buffer that takes into account the potential fluctuation of the process location. If one assumes, for example, that the process location can naturally fluctuate by 1.5 times the standard deviation, then only 99.99966% of all values would be within these 6 sigma limits. This still provides a sufficiently high level of security against making out-of-specification characteristics. We have already mentioned the terms spread and process location several times in connection with rejects. In this chapter, we will take a closer look at this connection. We'll stick with our example with the cylinder. Its lower specification limit is 60 mm. Its nominal size is 60.1. Since the nominal size is in the middle of the tolerance, this also corresponds to the target value. The upper specification limit is 60.2 mm. The mean, μ, of all measured values corresponds to the target value. This means the process mean is congruent with the target value. While this is desirable, it is seldom the case in practice. From a previous sample production, a standard deviation of 0.033 mm was calculated. So 3 times the standard deviation is 0.1 mm. This means that 6 times the standard deviation happens to be the width of the tolerance. As already mentioned, 99.73% of all values would then be within the specification limits. Conversely, this also means that such a process would produce 0.23% parts whose diameter is outside the specification. If the spread of a process is just as wide as the tolerance, then in statistical process control, this is called a potentially capable process. So far, we have concentrated on the spread of the values and assumed that the process mean is congruent with the target value. But what if this is not the case? We will look at that next. In the process shown here, the process location is shifted. The process mean μ deviates 0.06 mm from the target size. As can be seen here in yellow, this offset in the process location results in a significant proportion of rejects to be expected. Since, as already mentioned, in practice, the process location is never actually congruent with the target value. It may also not be sufficient if 6 times the standard deviation just so is the width of the tolerance. A further requirement must therefore be added. As we can see here, the process location is again congruent with the target value, but has a much smaller spread than the previous one. If the process location shifts, this does not lead to a significant increase in parts that do not conform to the specification. For this reason, so-called process capability indices are also determined in statistical process control. In addition to the spread, these also take into account the process location. In this example, this would be calculated from the difference between the upper specification limit and the process mean divided by 3 times the standard deviation and should not fall below a specific value. However, the topic of process capabilities is the content of another lesson. Here, the 2 processes just presented are compared again. Above, with a wide spread and the subsequently increased proportion of rejects when the process location shifts. Below a process with a small spread. A shift in the process location to the same extent does not lead to a significant increase in rejects. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. Confidence intervals are one or multiples of the standard deviation. To avoid scrap, the spread should be small in relation to the tolerance. The process mean can shift and lead to increased rejects. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye.